All right, so moving on, right, we've finished the first two topic areas. So atomic theory, periodicity, right, that will be on the test next week. We'll have a revision session in our last period of this week. For that, practice test was already up on Friday. Solutions are up there as well. So I'm doing this for Douglas's benefit so that he can not have to miss out on class. All right, metals. Thank you. All right, so our key knowledge, straight from our study design, we should be able to know some of these things. Common properties of metals, that they are lustrous. What does that mean? Shiny. Malleable, what does that mean? Right, bend or hammered into sheets. Ductility, what does that mean? Into wires, right? Heat and electrical conductivity in particular, what does that mean? Able to conduct electricity, awesome. Yeah, we've basically covered this already as part of our trends, right? So now we're going to talk a little bit more about metallic bonding model. Reactivity of metals we've even looked at, right? As we go down group 1, reactivity what? Increases. Same with group 2. Right, extraction process of a selected metal from its ores. We're actually going to glaze over that. It's not really that important, right? Experimental modification. So we will look at heat treatment and alloys. Who owns a bicycle? Good chance that you have an alloy frame, right? Steel is an alloy. When it says it's an aluminium frame, it's actually an aluminium alloy. Might be titanium. The only difference is if you have a carbon bike, that's actually a polymer, not an alloy. Right? Experimental modification, properties and uses of metallic nanomaterials. Again, that's something we will glaze over. Reactivities, right? We've looked a little bit at that. You might have looked at that in year 10. Water, acids, and oxygen. Metals are defined as elements that lose their outer shell electrons. So they become cations. Yeah, they become positively charged as they lose those electrons. Here was a question from last week. Are cations smaller in atomic radius or larger in atomic radius? Smaller is correct. They lose electrons. The remaining electrons have a stronger force of attraction towards the nucleus, and the ionic radius decreases. They're strong. They're hard. Hardness is a measure of a substance's ability to scratch another substance. Right? So something like diamond is one of the strongest substances we know. So the only thing to cut diamond is diamond itself. Nothing else will cut diamond. No. No. Depends on the size of diamond. You essentially have a large diamond and you cut it with a diamond chisel blade. Well, diamond comes as little pieces. Question. You probably can, but you'd need a fair amount of force, yeah? Simply dropping a diamond probably wouldn't be enough, yeah? Cool. So hardness is that ability to resist being scratched, right? So the harder the substance, the less easy it is for it to be scratched. A harder substance will scratch a softer substance. Strength is sort of a measure of how much of a load the object can take without deforming. High densities, right? We talked about densities. Recall that. Density equals mass over volume. That will be in your test next week. Gold, iron, mercury, right? Here is our buck in our trend. Mercury, liquid at room temperature. So it's the only thing to go against our metallic bonding model. Mercury, liquid at room temperature. All the others, solid, very high melting and boiling temperatures compared to similar substances. Group 1 and Group 2 tend to be softer metals with lower melting and boiling points. As we go across the periodic table, generally we see an increase in melting and boiling point. Look at a periodic table. Notice where gold is. Notice where silver is. So diamond in the form of carbon, yeah. Diamond is carbon, and we'll look at that. It's not actually that valuable. I don't find it that valuable.
Can you not make it in a...
Yeah, so you can get different coloured diamonds. They tend to have slight impurities in them because of what else is in there. So there might be minute amounts of different elements in it. You can get chocolate diamonds in Australia, as in chocolate colour. They're a brownie coloured diamond. Electrical conductivity, yeah, yep. Silver's a rather soft metal though, and it's slightly more reactive than gold, and so that's why gold tips are probably more useful than silver, because silver will tarnish. Generally, yeah, and that's because gold is more valuable than silver. Under, whatever, copper, generally.
If you find a massive diamond, how do you
Cut it. You can. You cut it with diamond. Right. We're not talking about diamond today, so let's just put diamond aside and talk about metals. So all the uses of metals can be linked with a given property. Building structures and carrying loads, right? That relates to its strength. Lightness and strength, right? Again, relates to its strength, relates to its hardness. Ability to form wires, that relates to metals' ductility. Electricity transmitted by metals, obviously that relates to metals' conductivity. Metals can be used to make diverse objects, that relates to its malleability, right? Even to the point of aluminium foil that we wrap up our food in, or put into our oven, or wrap our potatoes to give our baked potatoes, right? Aluminium used to be more valuable than gold. And fun fact is the top of the Washington Monument in the United States is this enormous piece of aluminium. But since the induction of electricity and our ability to electrolyze and essentially isolate aluminium in that way, caused aluminium prices to tank, and now it's a really, really cheap metal. Yes, Harrison? Yeah, not an alloy, but an aluminium oxide. So alumina is aluminium oxide, and we essentially have carbon and a heap of electricity. We melt the aluminium oxide, we reduce the metal using carbon. Carbon takes out the oxygen from the aluminium oxide, and we get liquid aluminium. Huge aluminium smelter down near Portland. Requires a large amount of electricity. Highest melting point, you can look at that later if you're interested. The model, as I briefly introduced last week, is this sea of delocalized electrons that surround fixed cations. Cation from the metal. The delocalized electrons are those outer shell electrons that are loosely bound to the cation. They stay in a three-dimensional lattice structure. The word lattice simply means a regular arrangement of particles. Any questions? So explaining their properties by using the model. High boiling point, a strong electrostatic force of attraction. Almost every type of bonding comes down to electrostatic. Electro means charge, static means still. So something about the force of opposite charges attracting towards one another. In the case of metals, it's the cation and the sea of delocalized electrons that hold it together. Conductivity, we explained that last week. It's those delocalized electrons are free to move. Free moving charged particles means a substance will conduct electricity. Malleability and ductility, the explanation of those is the same. If you put a force onto a metal, the cations will rearrange themselves, but the lattice will still remain held together. So we could represent that on the board. So we could have something like this. We apply a force to that, it shifts the layer across. Right, so we change the shape of the metal, but it's still held together. Limitations of the model is that we can't use the model to explain the range of different melting temperatures and densities, right? We know that melting temperature is a sign of an increase in force of attraction between particles. Between, say, sodium and magnesium, we could slightly explain that. It's got a higher core charge, more electrons are in the sea, and therefore a stronger force of attraction there. But it doesn't explain things like mercury or the fact that gold is over 600 degrees. It doesn't explain the difference in electrical conductivity. It explains conductivity as a general property, but not differences between them. Copper wiring is highly conductive, zinc is not. It tends to be used in dimmer switches. And we can't use the metallic bonding model to explain magnetism. Okay, might leave it there for today and talk about alloys in our next class. Any questions?